This is two charges, and these are the radiations encircling clockwise. There are also radiations counterclockwise, but we are looking at the clockwise radiations now. And we have electric fields and magnetic fields in the radiations. If we bring the charges closer to each other, you see that in this area we have radiations from both charges. And the radiation intensity from one charge is proportional to the electric field in that radiation, and the radiation intensity in the radiation from the other charge is proportional to the square of the electric field in that radiation. But the sum radiation here is proportional to the sum of the fields in square. And this equals the electric field from one radiation squared plus the other from the other. But we get an extra component here, which means that the total radiation here is larger than the sum of the radiations. And the same happens over here. We have the radiation intensity from charge 1 and we have from charge 2, and also here we have an extra term. So when the charges are like this, the total energy in this area is larger than the sum of the energies for each particle. In the area between the charges, the radiations are traveling in different directions, and they don't add. And of course the same happens with the radiations going in anti-clockwise direction. Energy is stored outside the charges. When we study the clockwise radiation from particle 1 and the anti-clockwise radiation from particle 2, we see that nothing happens outside the charges. The radiations are in different directions. But between the charges, there the radiations are in the same direction. The clockwise and the anti-clockwise direction go in the same direction, and in this area the electric fields are in opposite direction, meaning that we have to take the difference between the electric fields, and this means in this area the total radiation is less than the sum of the radiations. Now we have two cases. How much energy is stored outside the charges and how much is released between the charges. And this makes it very interesting. In the area outside the charges, this is the distance between the charges, energy is stored, and the closer the charges get to each other, the more energy is stored outside the charges. But in the area between the charges, energy is released. And this gives a total curve like this. When we add the two curves, we see that at large distance we have to add energy to press the charges together. But at some critical distance, suddenly more energy is released between the charges than is added to press them together, and then they are pulled together, the charges. So outside we have to press the charges together, and at a critical distance they are pulled together. And we call this the nuclear force that keeps the charges in the nuclear together, and this is the electromagnetic force at larger distance between the charges. And in the nucleus, the particles are kept together, but if we can add this energy to reach the energy needed to release the charges, then we can get this energy when we split the nucleus. When we take the nucleus and add the first electron, the positive nucleus, and add the negative electron, we will get a diagram like this, inverted compared to the first one. The electron is drawn to the nucleus, energy is released, but at a certain distance you need to add energy to get the electron closer to the nucleus, because then the total energy is larger than this. This is the point of minimum energy. And for the next electron, the point of minimum energy is, of course, on the other side of the nucleus. And when we add another electron, we can find another distance where the energy is a minimum. And that's where that electron will be located. In this picture of the charges, the positive charges and the radiations encircling the charges, I say that in this area and in this area, more energy is energy per volume is in these areas compared to what is coming into the areas. How is that possible? How can we have more energy over here than the energies coming into the area or releasing the area, going out from the area? Well, the only possible explanation is that the radiations are not traveling with the speed of light. C0, but they are traveling at a lower speed. Energy is coming in, and then they are traveling at a lower speed, and then more energy is in this area than per volume than is in the area surrounding in other directions. And the same is true in this picture here. Between the charges, the energy is lower than the combined radiations. And the only explanation is that in this area the radiations are traveling faster than the speed of light, the traditional speed of light. So at the outside they go slower, here in the middle they go faster, and if the speed of the radiation is changing, then this is the explanation of the curved space. Because we don't need a curved space if we can change the speed of the radiations. And this is also an explanation of what is happening just after Big Bang. An enormous amount of energy was produced and expanded in all directions, and it traveled so fast that it traveled at a speed much higher than the speed of light. And if the energy was in the radiations were traveling in antiphase and traveling very fast, the energy density would not be very high. This is the Earth, and this is some object. Here we have a force, the force of gravity. If we let the object go, it will fall down. Energy will be released. And this means that the total energy of the system, the Earth together with the object, will be smaller than when the object was up here. So the true definition of a force is delta energy with distance. The energy needed or the energy released when we move the objects in accordance with each other. This is the true definition of a force.